Greetings everyone, and welcome to this video on the Bonferroni method to correct for multiple comparisons. The previous video in this playlist focuses on why correcting for multiple comparisons is necessary. In this video, I will be discussing the Bonferroni method to correct for multiple comparisons. Usually when you run an analysis of variance and perform post-hoc tests in softwares like JASP, due to many comparisons being made between groups, such as pairwise comparisons, these softwares automatically correct for multiple comparisons using corrections such as the Tukey, Bonferroni, Sidak, Shefe, Home, and so on. Each of these have their uses, but the commonly used tests are the Bonferroni and the Tukey tests. Here I will show you how to perform the Bonferroni correction. You can apply the Bonferroni correction to p-values as well as confidence intervals. Let's say that we have three primary outcomes we want to study. In this data set, we have two groups of students, one group who were trained to give a specific exam and one group who were not trained. These are the three subscores which the students have obtained in this exam. So now we have three primary outcomes that we want to study with three continuous dependent variables and a binary independent grouping variable. In such a case, we would naturally consider using three separate t-tests. However, as we discussed in the previous video, due to inflation of the type 1 family-wise error rates, we need to control our alpha. Hence, we will use a smaller p-value as our cutoff for accepting or rejecting the null hypothesis. Using the Bonferroni correction, we will accept the alternative hypothesis only for p-values less than 0.05 divided by 3 or 0.167. How did we end up with this number? Simple. We are interested in studying three primary outcomes. So we divide our p-value set at 0.05 by 3, which is 0.0167. Now for the confidence intervals. We may simply adjust our confidence intervals as 100 minus alpha. When our alpha was at 0.05 or 5%, we had our confidence interval set at 100 minus 5, that is 95%. Now that our alpha is 0.0167, that is 1.67%, our new confidence interval limits need to be set at 100 minus 1.67, that is 98.33%. To see this in action, we will actually perform three separate independent samples t-test and get the mean difference values with confidence intervals. Note that the first p-value for scores 1 does not fall below our accepted p-value at 0.0167. So we immediately accept the null hypothesis for score 1 and say that the people who were trained did not score better than the people who were not trained. However, for scores 2 and 3, we can see that these p-values are less than 0.001. And even if we multiply both of these by 3, we will still get a p-value which is less than 0.0167. So we accept the alternative hypothesis for both of these scores and say that the people who were trained scored better than the people who were not trained. Now, we have obtained 95% confidence intervals for the mean difference. However, these are set at 95%. And as we discussed, we are not going to accept 95% confidence intervals because if you can see, these do not cross the null value of 0, the null value of the mean difference of 0. So there is a disparity between our accepting of the null hypothesis and the crossing of confidence limits. So we will now set our confidence limits at 98.3%, which we had discussed, and see. And immediately we recognize that these confidence limits have crossed 0, which is fine. So we accept the null hypothesis for scores 1, but for scores 2 and 3, they do not cross the null value of 0, and so we don't accept or we reject the null hypothesis for both of these scores. That's it for this video. Thanks for watching.